Okay, hi everyone. Let's go through the study guide, those 10 sample problems for the honors Q2 test. So starting with number 1 here. Metal absorbs 3.82 kilojoules of energy as a 61.9 gram piece warms up from 15 to 194. Calculate the specific heat capacity C. So the relevant formula here is Q equals MC delta T. Now you're used to doing this with water with values like 4.18 and things like 334 joules per gram, but this one doesn't deal with water, so we're actually going to solve for C. So C equals Q over M delta T. All right, so C equals Q, which is heat. Now that has to be in joules because well, I guess technically in this problem, I didn't specify what C needs to be in, but if we're following the normal the kind of historic traditions we've done in chemistry, it should be in joules per gram degrees Celsius. So let's convert these joules, kilojoules into joules. So I'm going to go 3,820 joules divided by the mass, which is 61.9 grams, and divided by delta T. So 194 minus 15 is 179 degrees Celsius. Okay, checking out our units, nothing cancels, which makes sense. Joules per gram degree Celsius. So 3820 divided by 61.9 equals, divided by 179 equals 0.345 joules per gram degree Celsius. Now you might say, hold on, shouldn't we use 2 sig figs because of the 15? No, because we didn't plug 15 in, we plugged in delta T, which was 179, which was 3 sig figs. For option 2, does this value, the C value of the metal, make sense when compared to liquid water's value? Yes, it does. Metals are always going to have very low specific heat capacities because it's very easy to heat a metal up or to cool a metal down. They heat up with very little energy added because they're great conductors. So I would expect a lower C value for metals compared to water, which has a very high C value. All right, question 2. What mass of nickel can be obtained from a 0.982 kilogram sample of NiNO3 3? You'll later learn that's called nickel 3 nitrate. Okay. So I'm given the mass of the sample, and we're looking for how much Ni could be obtained from that. So this is a percent composition problem. I'm basically finding what percent Ni is in that compound. Should be pretty simple. We just find the molar mass of the entire compound, and then we divide 1 nickel divided by that. So this is going to be the molar mass of 1 nickel, which is 58.69 grams, grams per mole, really. So adding this up, 58.69 plus, there are 3 N's plus 9 O's gives me 216.70 grams. That's really grams per mole. The units cancel anyway. So 58.69 over that gives me 0.2708. I'm going to call it 27.08% Ni. Notice I'm consistent with my sig figs there. I have 4 sig figs up top, 5 sig figs on the bottom, so I'm going to go with 4 sig figs. So that's the percent Ni. So to find how much Ni we could get, we're going to multiply our sample, which is 0.982 kilograms. That's going to be 982 grams times 0.2708, which is the percentage of that. So 982 times that percentage gives us 266 grams of Ni. And really, now that I think about it, I never said you had to answer in grams, so you could have kept it in kilograms and said 0.266 kilograms of Ni. Either one. Question 3. All right, a lot of background information here. So DDT, dichloro-diphenyl trichloroethane, was first chlorinated insecticide developed. It was used extensively in World War II to eradicate mosquitoes and spread malaria. Its use was banned in the US in 1978 because of environmental concerns. Okay, a lot of good background, not relevant to the question specifically. DDT is made of C, H, and Cl atoms. When 5.000 grams sample of DDT is burned in oxygen, we given the mass of CO2 and the mass of H2O that are obtained. Okay, so this is clearly going to be a combustion analysis problem. So the premise behind these problems is when you have combustion of a fuel, you're going to produce CO2 and H2O. Now, all of the carbon from our original sample ends up in the CO2, and all of the hydrogen from the original sample ends up in the H2O. So now that I know how much CO2 we got, I can backtrack to find out how much C was in the original compound. Same thing with H. I can find out how much H is in that H2O, and then I can backtrack to find how much H was in the original sample. How do we do that? Let's start with the C, the carbon. So it says we have 2.57, wait a minute, hold on. Whoops, right here. 8.692 grams of CO2. Now, how do I find how much C is in that? Well, I need to figure out the percent composition of C in CO2. So CO2 is, well, 1C, so 12.01, divided by, I've done this a million times, so I just have it memorized, 44.01. That's the molar mass of CO2. 12.01 over 44.01 gives us 27.29% C. That's the percentage carbon in CO2. Now, if I multiply my grams of CO2 by 0.2729, that would tell me how many grams of C are in that sample. And I don't want to cut sig figs here. It gives me 4. I want to maintain 4. 2.372 grams of C. Okay, we're going to do the same thing for the hydrogen now. So the problem says 1.142 grams of water, and I'm going to multiply that by the percentage of hydrogen in H2O. How do I find that? Well, there are 2 hydrogens in water. That's 2.02. And water is 18.02. 2.02 over 18.02 gives me 11.2% H. So that's the percentage hydrogen in water. So if I have 1.142 grams of water, I'm going to multiply that by 11.2% or 0.112 to give me, and really I guess I could go an extra sig fig here in the molar mass to be detailed. I'm going to go with just 4 sig figs here. 0.1280 grams of hydrogen. Okay. Now, often in these problems, we will subtract those two and find the amount of oxygen, because usually, well, I shouldn't say usually, but often the third element's oxygen. But in this problem, it's not oxygen, it's chlorine. So what it says is, let's see. Can we just subtract these to get the mass of chlorine? I think we can, right? So why does it need to give us the HCl? A second 5 grams simply was 2.571 grams of HCl. Maybe we can solve it 2 ways. Let me just quickly check this. I don't know why this is. I almost feel like I don't need that last sentence, so I'm questioning why it would be there. So HCl is going to be 1.01 plus 35.45. So it's 36.46. I'm going to do 35.45 over this to get 97.2% is Cl. I'm going to multiply 2.571 by that to get 2.500 grams of Cl. Now let's see, if I just subtract both of these out of my 5, am I also going to get 2.500? I think I will. So the original sample was 2.500 grams. no, sorry, that's not right. The original sample was 5.000 grams. If I subtract the 2.372 grams of carbon, and if I subtract the 0.1280 grams of hydrogen, yeah, okay. So I guess you can find the mass of the Cl in two ways. You can find it by just subtracting the carbon and hydrogen from this original sample, or what I said before was I looked at that sentence with the 2.571 grams of HCl. I worked out the percentage of Cl in HCl. I multiplied that by 2.571 and I got 2.5. So, okay, that threw me off because it usually doesn't give you two avenues for solving it. All right, well, now that we have grams, we're back in familiar territory. To find the empirical formula, we're going to turn all of these into moles. I'm just going to save some time writing this out. So hopefully by now you know you would divide each by its molar mass. So 2.372 grams of carbon divided by 12.01 gives us 0.1975 moles of carbon. 0.1280 divided by 1.01, or really I'm going to be more thorough there, 1.008 gives us 0.1270 moles of H. 2.500 divided by 35.45 gives us 0.07052 moles of Cl. Okay, now if you can spot the obvious ratio, you're done. I cannot spot the obvious ratio, so I'm going to divide each of them by the smallest of the numbers, which is the bottom number. Let me erase this stuff in blue over here, or blue and green. Okay, so I divide each of them by the smallest number, so that's going to force this one to become 1 mole of Cl. This one above it, 0.1270 divided by 0.07052 gives me 1.801 moles of H. And the last one gives me, interesting, 2.801 moles of C. So we're used to getting nice clean whole numbers here, in which you just write your answer, or 0.5, in which you double everything, or 0.33, or 0.66, in which you triple everything. We can extend that. If they end in 0.25, or even 0.75, you multiply by 4, you'll end up getting a whole number. In this case, I'm at 0.80. Think of it as like 2 4/5 and 1 4/5. If I multiply everything by 5, I should get nice clean whole numbers here. So 2.801 times 5 gives me 14.005, pretty close to 14. So I'm going to call it C14. For H, 1.801 times 5 is 9.005, close enough. H9. Cl times 5, Cl, yeah, that's good, Cl5. So that is my answer. Okay, and in fact, let me fact check this one on my phone here. Let's see, DDT formula. The DDT formula is C14H9Cl5. All right. Question 4. We have an ice cube at -11. It absorbs 39.2 kilojoules of energy. What's its new status? So I'm basically saying I don't want to give away the answer here where it's going to end up. I want you to find where it's going to end up. So if it's going to end up on one of the raised parts of the 5-part heating curve, I want you to tell me what temperature it's going to reach. Or if it ends on one of the plateaus, I want you to tell me how far along the plateau it is. In other words, what percentage? Is it 72% boiled? Is it 43% melted? So essentially you're finding where it's ending. So this is like what I call a bank problem. All right, so we're starting with a 102.3 gram ice cube at -11. So the first thing it's going to do is heat up to 0. Okay, it's not going to start melting yet. It's going to heat up to 0. To do that, it's going to have to use some of its bank of energy. How much? Let's solve for that. We're going to solve for Q. Q equals mc delta T. And for the first step, 102.3 grams times the C value of ice, which is 2.10 joules per gram degree Celsius. Your teacher might use a different value, like 2.06. Either of those will get you a minimally different answer, and it will be correct. And the temperature difference here is 11 degrees Celsius, giving us a value of I'm going to be very consistent and careful with my sig figs here. With 11 degrees, I'm going to go with 2,400 joules. Now that's how much energy is required just to bring it up to 0. We have to remove that from the bank and see how much we have left over. So the bank contained 39,200 joules. Hopefully you recognize that. Got to convert from kilojoules. We're going to subtract 2,400 out of there, leaving us with 36,800 joules left. Okay. What's the next thing that's going to happen? Well, now it's going to melt. Does it have enough energy to melt? Well, we can find out. So let's see how much energy it's going to take to melt. And if we have more left over, then we're good and we move on. If we don't have enough, then we know where we're ending. And now we can look a little more detailed in that. Okay, so let's see how much energy it's going to take to melt. Q equals M times HF or LF. 102.3 grams times 334 joules per gram equals 34,200. That's me being consistent with my sig figs, 3 sig figs, 34200. And you'll notice that it's going to pretty much deplete our bank. We have 36,800 joules left. We're going to subtract out 34,200 joules, leaving us with just, what's that, 2,600? Let me just confirm. Yeah, 2,600 joules left. Okay. Now, what's this H2O sample going to do now? Well, it's going to try to heat all the way to 100. Now, I guess I've done enough of these to just recognize that if we have 2,600 joules and we have a 100-gram sample, there's no way that thing's reaching 100 degrees. So I know it's going to end somewhere in region C. Now, if you want to be thorough, you can solve how much that would take, and I can do that real quick. 102.3 times 4.18 times 100 degrees Celsius is going to take 42,800 joules to go up to 100. Clearly, we don't have that. So now we're going to see how far along region C we're going to end up. What's our final temperature going to be? So instead of solving for Q, now I want to solve for delta T to end up getting final T. Delta T equals Q over MC, which is 2,600 joules. That's all we have left, divided by 102.3 grams. And the C value is 4.18 joules per gram degree Celsius, 2,600 over 102.3 over 4.18 gives us, checking sig figs, looks like 2 sig figs, 6.1 degrees Celsius. So we end up as 6.01 degrees Celsius liquid. That's our final temperature, final state of matter. And the last thing we need is a labeled 5-part heating curve. So we're starting at -11, ending at 6.1. So for a heating curve, temperature, energy added, up, flat, up, flat, up. We're starting somewhere down here in what I call region A. We're ending pretty low down there. We should only be about 6% of the way up in region C. So that would be our starting point and our ending point. Okay. Question 5. How many electrons are in 375 milliliters of water with a density of 1? Okay, so we're used to gram to molar particle conversions. We might not be used to electrons, but Well, you can figure out fairly easily how many electrons are in one molecule of water, and that can act as your last conversion factor. So let's work that out real quick. So water consists, it's H2O, right? So it's two H's and one O. So how many electrons are in each of those elements? Well, the atomic number on the periodic table is the number of protons, but that's also going to be the number of electrons because every element is neutral, it's balanced. If it's not balanced, it's an ion, but this is not. So I have two H's, each of which is one proton and one electron. So that's two. I have one oxygen, which is atomic number 8. I think I realized I made a mistake on my written entry. I gotta fix. Atomic number 8, which has 8 protons and 8 electrons. So H2O equals 10 electrons. E with a little superscript minus is electrons. I don't know why I'm second guessing myself on that. Yeah, no, that's correct. So 8 electrons in the oxygen, 2 electrons in the 2 hydrogens. By the way, that's not the same thing as valence electrons. I'm saying total electrons. So for this problem, we're going to go with our starting point, which is 375 milliliters of water. Let's turn that into grams. So 1.00 gram per milliliter. If you want to even just write it originally as grams, you can do that. All right, now I'm just going to keep going right down the line. This will give us our starting grams of water, which is obviously going to be 375 grams. To take that into electrons, I need to take it first into water molecules. So to do that, I need to go to moles. So times 1 mole over the molar mass of water, which is 18.02 grams. And then we're going to multiply that by 6.022 times 10 to the 23rd over 1 mole. Now, what's the unit after this? We sometimes put atoms, sometimes put molecules, sometimes put, other things. Well, the unit of this is really whatever the molar mass is of. So 18.02, that's the molar mass of what? Water, a water molecule. So in this case, this here is molecules, H2O molecules. It's not electrons, it's not atoms, it's H2O molecules. Now, what do we know right up here? We know that one water molecule has 10 electrons, so we can multiply this by 10 electrons per H2O molecule. So milliliter cancels milliliter, gram cancels gram, mole cancels mole, H2O molecule cancels H2O molecule. See how the units always beautifully work? Follow those along and you'll be just fine. 375 times 1 is unnecessary, divided by 18.02 times 6.022 E23 times 10 gives us 3 sig figs, 1.25 times 10 to the 26th electrons. And yep, I made a mistake in my answer. I gotta fix that. I said there were 16 electrons in water, in oxygen, because I'm so used to oxygen being 16, but that's not 16 electrons, it's 8 electrons. Question 6. All right, so this looks like a hydrate problem. So a hydrate is when you have water molecules kind of surrounding a compound but not bonded to it. And if you heat that compound up, that water will boil away, leaving just what's called the anhydrous salt, or the original compound. So we're trying to figure out what mass percent of the hydrate is water, and we're solving for X, which is the number of water molecules surrounding each unit of that hydrate, or of that anhydrous salt, really. So how do we do this? Well, we need to know the mass of the water and the mass of the anhydrous salt. So we start with 5.459 grams of hydrate. And when that's heated, 2.583 grams of anhydrous salt remain. Now I'm going to write the anhydrous salt as its compound, which is KAlSO4-2. That's the anhydrous salt. So what's the difference? Why did the mass go down? Because the water boiled away. Well, how much water? 5.459 minus 2.583, which gives us 2.876 grams of water. Okay, so again, the hydrate consists of that many grams of anhydrous salt and that many grams of water. So to find the mass percent of the hydrate for water, it's very easy. It's going to be 2.876 grams of water divided by 5.459 grams of hydrate. Let's see what we get. 52.68% water. Okay. I need a slightly different answer. Okay. I think I know why. Now, to work out the X, we're looking for the moles of water. So I'm going to turn my water into moles, and I'm going to turn my KAlSO42 into moles. So for the water, I'm going to divide that by 18.02. So 2.876 divided by 18.02 gives me 0.1596 moles of water. And for this one, it's going to be a tricky molar mass. So 1 potassium plus 1 aluminum plus 2 sulfurs plus 8 oxygens. I got 258.22. So when I go 2.583 over that, I get 0.01000 moles of KAlSO42. Kind of out of room there. Okay, so how do I find this? Well, I need to now find the mole ratio. So I'm going to divide them both by the smaller one. So divided by 0.01000 gives me 1 mole of this. And divided by 0.01000, that's really just like multiplying it by 100. That's going to give me 15.96 moles of this, which is really close to 16. So that's my number. X is 16. So really the formula for this hydrate is going to be KAl parentheses SO42 dot 16 H2O. Number 7. How much heat's given off when a 438 gram sample of 20.0 degree water is cooled and eventually reaches -21? All right, so this should be a pretty straightforward problem. I want to start with the 5-part curve for this one. Up, flat, up, flat, up. Temperature, energy added. So we're starting at 28 degrees. That's going to be about here. We're ending at -21, so somewhere down here. So that's our starting point. That's our ending point. And I can tell this is going to be a 3-step problem. It's going to cool down from 28 to 0. Then it's going to freeze. Then it's going to cool down from 0 to -21. So we're going to figure out how much energy was given off in each of those steps. So step 1, Q equals MC delta T, which is 438 grams times 4.18 joules per gram degree Celsius times the change in temperature from 28 down to 0. We can call that negative 28.0 and end up with negative energy, which is fine. That's energy released. Or we can just treat it like absolute value and get the answer in the end. I'm just going to do the latter. I'm going to treat it as positive. 438 times 4.18 times 28, 51,300 joules. That's the joules released. You can also have that as negative 51,300 because negative energy is associated with energy being released. Next step, it's going to freeze, which is going to give off even more energy. Q equals M HF, 438 grams times 334 joules per gram. 3 sig figs, 146,000 joules. Last step, now that it's frozen, it's solid, it can now start cooling down to -21. So MC delta T again, 438 grams times the new C value for solid, 2.10, or 2.06 if you use that one, times 21.0 degrees Celsius. Again, you can do negative 21 if you want. 438 times 2.10 times 21 gives me 19,300 joules. So I'm going to add up my three numbers here, 51,300 plus 146,000 plus 19,300. Since I'm adding, I'm now limited to places. So I have the hundreds place, the thousands place, the hundredth place. I can go with the thousands place, the least specific one. So my final answer is 217,000 joules are released. Now, just a note, if you ended up making those delta T's negative, you also need to make your middle Q value negative, where I guess in that case, you would do like, I guess, negative 334 joules per gram, because that's going to be the energy released. Just they're either all positive and you end up with a positive value, or they're all negative and you end up with a negative value, but it should be 217,000 regardless. Question 8. Allison, the compound that gives garlic its characteristic odor has that percent composition. What's its empirical formula? All right, so pretty straightforward EF problem. So when you're given percentages, you just assume it's 100 grams and make them grams, turn them into moles, look for the pattern. 6.21 grams of H, 44.4 grams of C, 9.86 grams of O, 39.51 grams of S. I hope you'll forgive me for skipping writing the setups just to save some time here. 6.21 divided by 1.01 gives me 6.15 moles of H. 44.4 over 12.01 gives me 3.70 moles of C. 9.86 divided by 16.00 gives me 0.616 moles of O, and 39.51 over 32.07 gives me 1.232 moles of S. Notice I was very consistent with sig figs. When it gave me 3, I gave it 3. When it gave me 4, I gave it 4. We look at these and we asked, can we see the obvious ratio? I cannot, so I'm going to now divide them all by the smallest number, which is this one, 0.616. We're going to see what we get. All right, so I can tell that top one is going to be pretty close to 10. Yeah, 9.98 moles of H. 3.70 over 0.616 gives me 6.01. I like seeing that. This one is obviously going to be 1.00. And this one looks like 2. 1.232 over 0.616. Yeah, perfect 2. All right, so I'm pretty happy with these ratios. Looks like I don't need to apply any sort of multiplier here. It's just going to be a 10 to 6 to 1 to 2 ratio, giving me H10, C6, O, S2. And you can Google that compound and check to see if that's correct, and I believe it is. Question 9. 225 mLs of water at 25 C are mixed with 85 milliliters of water at 89 C. What's the final temperature? So this is a classic mixing two water samples and finding the final temperature. The premise behind this problem is that the heat given off by one equals the heat absorbed by the other as they reach equilibrium. Or in other words, Q equals negative Q, where the heat released by one, which really is the negative Q, equals the heat absorbed by the other, which is the positive Q. Q equals negative Q. So what is Q? Well, Q equals MC delta T of one. So that's going to equal negative MC delta T of the other. Now at this point, we can cancel out the C's on both sides because they're the same. And the other thing I'm going to do is rewrite delta T as T final minus T initial, because that's going to help us with this. So the C's are going to be gone, and delta T is going to be written as TF minus TI, giving us M times TF minus TI equals negative M times TF minus TI. And now we just plug the numbers in. Now my students know I'm a stickler for always including units. Every time I write a number, I write a unit. This is the one exception I make for that, because when you do put units in here, it becomes very much clogged with very strange units. Now you'll end up getting the right answer in the end, but it's in my opinion, it bulks the problem up unnecessarily. So I'm going to go numbers only, and I'm going to plug it in, and we're going to solve for T final. Okay. So on the left, I'm going to go with my first one here. So the mass is 225 milliliters, which is going to be the same as 225 grams. So I'm just going to write 225 times T final, that's what we're solving for, minus T initial is 25. And that's going to equal the stuff on the right. Negative M, which is 85 grams, times the same T final minus the different T initial. This one started at 89 degrees Celsius. And now it just becomes an algebra problem. So we're going to distribute the 225 in there. So it's going to be 225 times T final equals 225 times negative 25, which is not equals, minus 5625 equals, we're going to distribute the 85 in now. So negative 85 times T final, negative 85 times negative 89 is going to be a positive value, so plus 7565. All right, let's bring my TFs onto the left side. Let's bring my loose numbers onto the right side. So I'm going to go 225 plus 85, which is going to give me 310 times TF equals, let's bring the negative 5625 over and add that to 7565. Again, it's just basic algebra here. 13,190. Let's divide both sides by 310, giving us a T final value. Let me check my sig figs. 2 sig figs. 43 degrees. And I'd say that makes sense. I mean, one sample started at 25, the other sample started at 89. So notice we're not meeting in the middle, but I wouldn't expect them to meet in the middle because the one at 25 has like 3 times more water. So it should meet a lot closer down to 25 than up, at the halfway point. All right, last one. A cube of sodium has a length of 1.25 inches. How many atoms are in the cube? I like this one. It gives the density of sodium and it gives the inch to centimeter conversion, in case you forgot that. So really this is a gram to mole to particle conversion with just a lot of sort of fluff. So we're looking to find atoms, and we can start by finding the mass of sodium, just with a little bit of extra. Okay, so if we have a cube that has a length of 1.25 inches, we can figure out the volume of the cube. Volume equals 1.25 inches cubed, right? Because it's just length times width times height, and if they're all the same, it's going to be like that. And by the way, make sure you don't do 1.25 inches cubed. It's 1.25 inches cubed. So I'm going to go 1.25 to the third power, which gives me 1.95 inches cubed as my volume. Okay. Now I'm going to have to take this and find grams. Now it gives us the density of sodium in grams per centimeter cubed. So I'm going to have to turn this into centimeters cubed, which we can do easily. 2.54 centimeters per inch, and then we cube that or write it 3 times. And we can solve now, or let's just keep going. Let's take our centimeters cubed and convert it directly into grams by turning the density into a conversion factor. So this is going to give me centimeters cubed on top. I'm just going to multiply this by 0.968 grams per centimeter cubed. That's the density. Now that we have grams, we need to go to number of atoms, so we have to use moles as the middleman. So times 1 mole over the molar mass of sodium, which is 22.99 grams. That's going to give us moles. Last step, Avogadro's number. And the unit here is atoms, since that's the molar mass of sodium, which is atoms. Let's confirm that the units are all correct. Cubic inches will cancel cubic inches. Cubic centimeters will cancel cubic centimeters. Gram cancels gram, mole cancels mole. We're left with atoms. Let's see what we get. 1.95 times 2.54 to the third times 0.968 divided by 22.99 times 6.022 E23 gives us, with 3 sig figs, 8.10 times 10 to the 23rd sodium atoms. Okay, hope this study guide helped. Remember, if you did these 10 questions, you should be in good shape. Not that does not mean that you know everything. There's of course a lot of qualitative stuff on your quarter test as well. I picked really the math problems to work out here, and you could of course see some math problems that are not like the ones here. So this is sort of like a jumping off point to just kind of remind you of how to do some of these problems. Okay, good luck everyone.